This is the Milwaukee 18 volt scraper. Well, it doesn't work for shit on painted metal. Let's see what else it can't do. Hey, urethane rubber on wood, not bad. Urethane goo on Bridgeport milling machine. Not bad, not great, not bad. How about a decal? Yeah, not bad. I guess it worked almost as good as a razor blade. A speed controller that goes from 2 all the way, not to 10, not to 11, but 12. Somebody's a Spinal Tap fan. Cue clip.
What we do is if we need that extra push over the cliff, you know what we do?
Put it up to 11.
11, exactly. One louder.
Why don't you just make 10 louder and make 10 be the top number and make that a little louder?
These go to 11.
Okay, well now we got to take it apart to see how it controls the speed. That's weird. There's a little plastic condom over top of this nice aluminum casting, maybe a magnesium casting. I guess so that they can put a little LED in there. Oh, weird. Alright, we're in. And here's the... Oh no! Fuck! Well, they're getting wise to me, boys. See this whole circuit board? It's all been potted. It's epoxied. There's no way in there. Son of a diddly. This is interesting though. Here's the on-off switch, just a choochie little switch here. Clack, clack. Nice positive snap action though. And here's the circuit board, potted. And this is a no, not an H bridge. This is a half bridge configuration. 2 MOSFETs, which are electrical switches, mounted onto an aluminum heat sink. And here's your speed controller here. It's just looks like a rotary switch. Nice solid detents. So this is neat. It looks like a big brushless motor, but it's actually not a brushless motor. It's a brushed motor. The brushes are enclosed in this assembly. And out the back end on the tail end of the shaft here, looks like we have a little ferrite magnet, some sort of magnet on there. And I would assume that there's a Hall effect sensor that's sensing the change in magnetic field on this guy, and it's feeding back into the microprocessor so that the microprocessor can vary the pulse width that it's turning off and on these MOSFETs, and that'll vary the speed depending on where this input is. So that's interesting. Not much going on here. A little, just a little DC motor, and this is actually on a on an offset bearing here. The shaft has a offset, so this bearing, I'm sure when this spins you can see that. So when this spins, this bearing actually oscillates around, engages on this little guy here, spins that back and forth. And that's well lubricated with lots of axle grease, and the quick release with the detent there. So the quick release, all it does is you thread this collet screw in there and then pull it back, and it pulls it in tight and clamp it. I give you the broad strokes now. I will get to the wheres and the Y2s of all this electronic goop. You're going to select your speed with this speed select switch. It's got nice detents. So the microcontroller is going to read the position of that, and it's going to vary the pulse width that is turning off and on these MOSFETs. These are just little switches, electrical switches. And depending how long it turns on and off in that pulse width modulation, say it's 0%, then you're going to get 0 volts to the motor. Say it's 100%, then you're going to get full voltage, 18 volts. Now the thing is, there is feedback, which, yeah, that's magnetic. There's feedback which is not in the drills, and that makes it a little more complicated, a little more interesting. So there's feedback going back into the microcontroller through a Hall effect sensor. So the Hall effect sensor is measuring the change in the magnetic field, north-south, and it can count how fast that motor is turning. So the Hall effect sensor is feeding back into the microprocessor to make sure that it's going the speed that we've set here. I guess because say we have 10 volts going in here with no load, it's going to go a certain speed, but there's a fair bit of torque required to get this to move back and forth. And if you want a constant speed, you need to allow for the motor slip under load. Now, electric motors, in order to develop torque, there needs to be some slip, which means that it's going slower than 10 volts feeding into it would make it normally go under no load. Sorry to overcomplicate that. But anyway, at 10 volts, it's going a certain speed. Then under load, it needs to slip to develop torque. So it's going slower than it normally would. And we feed that back in so that the microprocessor can increase the pulse width here to increase the voltage and bring up the RPM to where it should be. Now, we don't have that feedback mechanism on the drills, and it would be a nice feature to have. That way you'd always have the same turny speed regardless of how hard you're pressing. Okay, so I got her back together. I'm gonna give her a try here. Jesus fuck. Goddamn Widowmaker. Holy. You gotta watch that. It sticks on. You put the no good. Jesus. Ugh. This thing's horrible. I mean, even the most casual of observers can see that there's no way to clear the chip out of the gullet once you get to a certain depth. I mean, I don't know if you're gonna have to saw like this. I don't know, man. This kind of useless. It's a multi-tool, and sure, it does a lot of different things, I guess, but it does all of those things pretty half-assedly. And there's a lot better tools to do most of the jobs. I mean, the only thing I can think of is maybe if you do a lot of mill work and you got to cut, I don't know, door jambs or something, or you're a fiberglasser maybe. As far as a home shop or machining or metalworking, anything like that, don't buy it. It's friggin' useless. Yeah, even the sanding is going to be crappy sanding. I mean, you're way better off getting a cordless sander to do this. One of those little mouse things. I mean, you can buy one for $30 because it's just going to oscillate. It's not oscillating. It's just chooching back and forth like this. That's no good because, yeah, garbage. Multi-tool, I deem thee garbage.